In this video, we are going to discuss basic concepts about population and sample. Population is a group of individuals who have something in common. We may be interested in some properties about certain group, which we call target population, that cannot be observed completely. For example, all registered voters in Thailand, or all Hong Kong citizens who play golf at least once per year, or all neurons from your brain. Since we cannot get information for every individual of these populations, we have taken sample, which is a part of target population. Sample is a small group of population. It is a representative of the population. Hence, it has to be randomly selected. This process is called random sampling. There are two kinds of sampling, called sampling without replacement or with replacement. Depending on whether you put the select individuals back into population before you select the next one. In a sampling without replacement, an individual is randomly selected from the population. The next individual will be selected without putting the previous individual back. Every individual is selected from a different pool. If the population size is very large, this method is better because it can generate a random sample with different individuals. There is another kind of sampling method, sampling with replacement. A randomly selected individual will be put back before the next individual being selected. Hence, it is possible that the same individual can be selected more than once. When the population is small, this method can make sure that everyone in the population has the same chance being selected. In this example, we first create a blank data frame, and we create a new column in this data frame. Name the column as population. Then I run this Python code to perform sampling from the population by drawing 5 individuals randomly without replacement, and store them as a sample without replacement. In pandas, we can use method sample to get the samples. Here, the keyword replace equal to false means the sampling is a sampling without replacement. We can define replace equal true to perform sampling with replacement. Here are the results of 2 samples. You can see that for sampling without replacement, which is on the left-hand side, there are no duplicates individuals found. As we can see, there are no duplicate index numbers either. However, on the right-hand side, which is sampling with replacement, it is possible to see the same individual is drawn for multiple times. Besides population and sample, there is another pair of concepts, parameter and statistics, of which are very important in characterizing population and sample. Parameter is a characteristic or summary number of population. Statistic is a characteristic or summary number of sample. For example, mean, variance, standard deviation of population are characteristics of population. Once target population is fixed, these summary numbers will not change. Sample also has mean, variance, and standard deviation, but their values changes in different samples, even if they are drawn from the same population. Let's print out the parameters of population, which we have just created. We can calculate mean, variance, and standard deviation using DataFrame methods .mean, .var, .std. The mathematical formulas for mean and variance are given. In calculating VAR and STD, we set the keyword DDOF as 0, which means The denominator of population variance is n, which is the number of a population. Dot shift, as described in previous module, offers the size of data frame in rows and columns. We use dot shift 0 to display only the number of rows. Also, these methods can be applied to compute statistics of samples. First, let us get a sample with size 10 from population using replacement. The sample and the sample variance, standard deviation, are printed out. Notice that when we compute the sample variance and STD, we need DOLF equal to 1. It means the denominator of the sample variance has to be n-1 instead of n, which is the sample size. To understand why the denominator of sample variance is n-1, let us generate 500 samples, each sample with size equal to 50. We calculate the sample variance for each sample using n and n-1 as denominators. You find that the real population variance is 571.8. As you can see, the average of sample variances using n-1 is closer to population variance than using n. The average of sample variance using n as denominator is always smaller than population variance, with some mathematical reasons. n-1 in fact is called degrees of freedom for sample variance. There is another explanation why sample variance is divided by n-1, which is the degrees of freedom. Degrees of freedom is the number of values used in calculation that are free to vary. If we use the sample mean to compute the sample variance, we will lose 1 degree of freedom. For example, sample size equal to 3, sample mean equal to 100 is used in computing sample variance. We can choose 2 individuals independently, for example, 90 and 80 in the table, but the third is not free to vary because of constraint of sample mean. The only choice for the third number is 130. When we compute the variance, using degrees of freedom is better than using sample size, in the sense that the average of estimator will be equal to population variance, which is called unbiased estimator. In the next video, we will talk about distribution of sample statistics.